and welcome, class, and it's going to be a great day. We are finally starting Chapter 8, and what this signifies is that we are finally talking about chemical reactions. So we've seen a couple of reactions already in the lab, but we haven't explicitly talked about chemical reactions, chemical equations, stoichiometry, any of that good stuff. So that's what Chapter 8 is all about. This is a pretty short chapter since most of this is general review if you've taken any type of chemistry course in high school before. If you have not, then no worries, it's all fairly intuitive and we're still going to be laying everything out as explicitly as I normally do. So let's just get started. Alright, so what is a chemical reaction? A chemical reaction, by definition, as we've seen before, this actual specific slide before, but it was like way back in Chapter 1, a chemical reaction is a transformation of one or more substances, which we call the reactants, into one or more other substances, which we call the products. A chemical reaction is represented by a chemical equation. So a chemical equation, we can see an example down below, is a combination of like chemical formula on the left-hand side of this arrow representing the reactants. The reaction arrow itself represents the passage of time, so it's like the before and after. Our products are illustrated or, written here on the right. So these are the products. So in order to interpret this chemical equation, we would say that CH4, when combined with 2 parts oxygen, is going to, after the chemical reaction is finished, produce 1 part carbon dioxide and 2 parts water. The stoichiometric coefficients that we have present out in front, this is our technical term. These are not just big numbers. These are not just any coefficients. These are stoichiometric coefficients. These represent how many of each of the molecules we have in the actual chemical reaction. We need to make sure that the coefficients out in front help to balance our chemical equation to make sure that conservation of mass is being kept. We need to be able to end with the same amount of elements that we started with. So here we can see that we're starting, for instance, with 1 single carbon atom, and on the product side, we also have 1 single carbon atom. Similarly, we start with 4 hydrogens, and we end with 4 hydrogens. So each individual molecule of water contains 2 hydrogens, and we have 2 molecules of water. This means that we have 4 total hydrogen atoms across the entire product side. Last but not least, we have 4 total oxygen atoms. We can conclude this because each oxygen molecule contains 2 oxygen atoms, and we have 2 of those oxygen molecules. On the product side, there are 1, 2, 3, 4 oxygen atoms, meaning that all of our oxygens are also being taken into account. So we have perfect conservation of mass according to this chemical equation, and this equation represents the overall reaction that we would expect to physically see. Alright, so let's learn how to use these stoichiometric coefficients for ourselves. We must adhere again to conservation of mass. Because matter can neither be created nor destroyed, it can only be transformed, we have to make sure that all of our atoms that were present on the reactant side of an equation are also going to be present in some form on the product side of our equation. In addition, a chemical equation tends to list out the phases that our materials exist in order to give some context for the equation. For example, here, there are G's in parentheses following after each of our molecules. This G, as we would expect, knowing that it's supposed to represent a phase, stands for gas. So it's G for gas, L for liquid, S for solid, and AQ for aqueous. So we're going to see more about aqueous solutions in Chapter 9. It's going to be a really prevalent phase for our matter to exist in general chemistry and in chemistry in general. So we're going to get used to seeing AQ for aqueous as well, and we'll talk more about it later. For now, just know that what this equation represents is we're going to take gaseous oxygen mix it with gaseous nitrogen monoxide, and after some time has passed, we're going to get some gaseous nitrogen dioxide. The question is, how many parts? How much do we have to mix together? Well, I like, personally, to set up my equations to be balanced like so. I like to list out underneath the chemical equation, let's say here on the left-hand side, each of the elements that are present inside of the chemical equation. So we can see that we have some nitrogen present, we have some oxygen present, and I treat each of the elements as they are listed in the equation up above, almost like column headers. Now, this approach may seem kind of like extraneous or superfluous for simple chemical reactions, but I like personally to get into like this more generalized habit for one reason. Just, you know, I like to showcase it in case no one's ever seen balancing chemical equations before. That way you're not so caught off guard and you have a really nice tool at your disposal. But second of all, we aren't going to only be working with simple chemical equations, and it can be nice to have more of a generalized form, you know, to see how it works in these simple cases so you actually know how to use it in the more advanced cases. All right, so with that kind of disclaimer out of the way, let's balance this chemical equation. So underneath our oxygen header, I would say that I have no nitrogens and 2 oxygens, and the 2 is coming from this subscript right here. Underneath the nitrogen monoxide, I have 1 nitrogen as well as 1 oxygen. And these are all on the reactant side. So I also like to draw this kind of bold arrow, or bold double line, or a bold line in general underneath this arrow in order to like really help me to visualize where the reactants are the reactants and where products are products. Underneath the nitrogen, I will write a 1 because we have 1 nitrogen, and a 2 because we have 2 oxygens. Now our goal, in order to balance this chemical equation, is to make sure that every row on the left-hand side, so on the reactant side, adds up to the same number as is present on the right-hand side or the product side. So if we observe nitrogen, it appears as though we have 0 plus 1, so 1 nitrogen on the reactant side. We can visually see that on the chemical equation as well. And we have 1 nitrogen on the product side, so everything here seems to be balanced. When we turn our attention to the oxygens, however, we can see that there is a total of 3 oxygens on the reactant side and 2 on the product side. This means that we do not have the same number, and we're going to have to start fiddling with things to get the same number of each element on the reactant and the product side. Well, since we have a total of 3 oxygens currently on the left and 2 on the right, this means that there's not one way to like multiply one number into the other. So it's going to be a good idea to again, kind of visualize, break down where is the sum coming from. How can we either turn this odd number 3 into an even number, or would it be easier just to like cross multiply, right? Like scale one up by a factor of 3 and the other up by a factor of 2. Well, in observing the actual layout for our chemical equation, we can see that the oddness of our oxygen count is coming specifically from nitrogen monoxide. So if we want to remove the oddness and turn it into an even number so our products can scale into it, all we're going to have to do is add a big coefficient of 2 in front of the nitrogen monoxide. What this does is gives us another nitrogen and another oxygen. So yes, the total now on the reactant side is scaled up compared to the product side, but what's kind of cool is the nitrogen to oxygen ratio right now on the reactant side is a 2:4, which is exactly a whole numbered multiple of what we have on the product side, which is a 1:2. This tells us that all we have to do is scale up the product side by a factor of 2, and everything should now be equal, since we have 2 nitrogens and 4 oxygens on both the reactant and the product side. So this is how we can go about balancing our chemical equations, kind of laying out in an organized manner how much of each element we have on the reactant and product side, and then just messing with the numbers. There are some like general flows and patterns that you'll become accustomed to, but other than that, it's not like there's one really nice equation where you plug numbers in and suddenly your equation's balanced. So we're gonna have to get some nice practice kind of like breaking down what we have in front of us, balancing the equation, and then observing critically to make sure that it is actually balanced at the end. All right, so let's get some practice. I want you guys to try your hand at balancing these two simple chemical equations. One is the combination of lithium and fluorine to give us lithium fluoride, and the other is a rearrangement reaction. It's a little bit more complicated in appearance, but it's not too bad to balance. So I want to give you guys the chance to try that now. All right, welcome back. So in order to balance these chemical equations, we can see, and I'm going to lay it out using like my more explicit method. If you're a little bit more, let's say, experienced and you already kind of see the patterns and know how to balance these equations without this method, that's totally fine. We're still going to come to the same answers at the end. So for those who are a little bit less experienced, we're going to walk through this from the beginning because I don't want to leave anyone behind. Let's lay out how many in our first equation lithiums and fluorines we have. All right, and again, we're going to treat each of these elements kind of like column headers. So the question is how many lithiums? We have 1 lithium, no fluorines in our first species. We have no lithiums and 2 fluorines in our second species, and 1 lithium and 1 fluorine in our third species. Now this equation is a little bit more straightforward to balance because we have on the reactant side like pure substances. So it's a little bit easier to kind of parse out and like scale up and scale down. So you'll see what I'm talking about in a second. If we start comparing our numbers, it looks like the lithium is balanced. However, the fluorine we can see is not. There are 2 fluorines on the reactant side and only 1 on the product side. So let's scale up our lithium by a factor of 2. So that's going to give us 2 lithiums and 2 fluorines on the product side. Check, fluorine is good. If we compare our lithium again though, we're going to have to scale up the lithium now on the reactant side also by a factor of 2. And this is going to completely balance everything. 2 lithiums and fluorines on the reactant side, 2 lithiums and fluorines on the product side. So our overall balanced chemical equation looks like 2 lithiums in a solid form. Add that to a single fluorine molecule in gaseous form. And this gives us 2 lithium fluorides in solid form. All right, our second chemical equation here looks a little bit more complicated, but here's a little bit of a shortcut. Since in the chemical equation, we can see we're working with silver, which is an element, zinc, which is an element, and nitrate, which is a polyatomic ion, let's observe on the product side if our nitrate, the polyatomic ion, has changed form at all, like if it's broken up, if the nitrogen's no longer with the oxygen. Well, on the product side, we can see the nitrates are still in one piece. This is actually really useful for us. And the reason why is, since we need to break down all of the elements that we have, like let's say the silver and the zinc, we can treat the nitrate like one big group, like one big atom, since it doesn't change form from the reactant side to the product side. It only changes what the actual nitrate is linked to. This means that we don't have to take into account the nitrogens and the oxygens separately. It saves us on a little bit of work. All right, so let's treat again each of these groups like column headers with our reaction arrow designating products versus reactants. In our first species, we can see we have 1 silver, no zinc, and 1 nitrate polyatomic ion. And of course, with our zinc, we have no silver, 1 zinc, and no nitrates. On the product side, we have 1 silver, no zinc, no nitrate, as well as in our last species, no silver, 1 zinc, and 2 nitrates. So the presence of this 2 on the nitrate is our first clue that there's any type of discrepancy, because it looks so far like the silvers and the zincs have equal numbers on each side. So let's start by adjusting the nitrate values by adding a coefficient of 2 on our silver nitrate. This is going to scale up not only the nitrate, but also the silver, meaning that in order to balance the silver, we're going to have to turn our attention to where silver is present on the product side and add a coefficient of 2 in front of that as well. So even though the equation looks, in terms of chemical composition, a little bit more complicated, it was actually pretty straightforward to balance, especially if we take the nitrate into account as a unit. This is going to save us on a little bit of time and help us with clarity. Now here we have examples of the 5 different forms that chemical equations can kind of, start to look like. The different forms that chemical equations can take, to state it more concisely. We are going to break down what each of these terms means just by looking at a corresponding chemical equation. So this might be like, oh my gosh, there's so much on the slide, but we're just gonna break it down piece by piece. So the 5 different types of chemical reactions that we can discuss, at least at the general chemistry level, start finding some patterns, are synthesis, decomposition, single displacement, double displacement, and my personal favorite, combustion. So let's just start with synthesis, and then we're going to work our way down, breaking down the definitions of each of these reaction types by observing a corresponding reaction. All right, so synthesis by definition is a reaction that starts with 2. So we start with 2 or more species, and we end with 1. End with 1. Or at the very least, we end with less than what we started. End with 1 or less than what we started. So if we started with 3 species in a synthesis reaction, we might end with 2, we might end with 1. If we start with 4 different species, we might end with 3, we might end with 2, we might end with 1. But the point is that we are taking a larger number and squishing them down into a smaller number. We are synthesizing a lesser number of products. So for example, in this specific equation we can see here, we're taking hydrogen and oxygen and smooshing them together to make water. So even though we are starting with 1, 2 different species, and we are still adhering to the conservation of mass, we are creating chemical bonds between these 2 different species to create 1 molecular product. And this is the most common form for synthesis, if we start with 2 or 3 and we end with 1. All right, decomposition is sort of like the equal yet opposite version of synthesis, where we can see here we start with 1 and we end with 2. Start with 1, end with 2. And we might end up with more than 2, and that's totally fine, but the purpose here, or the kind of like takeaway message, is with decomposition, we start with 1 reactant or 1 type of reactant, for instance here, sodium chloride, and our products are going to be the individual pieces that were inside of the molecule. So we can see here we're decomposing salt to make sodium and chloride gas. So that's why this is called a decomposition reaction. We are decomposing the 1 and turning it into its many pieces. The next 2 types of chemical reactions we have to talk about also kind of work together. The first is single displacement, and the second is double displacement. Single displacement is what happens when we swap out one, let's say, cation for another cation, or swap out an anion for an anion. So for instance, if we observe the reactant side of this reaction where we have aqueous cadmium and we're mixing it with copper chloride, the product side we can see we have cadmium chloride and a resulting copper. What we have done effectively is take these 2 metallic species and swap them. So this is a single atom that is being displaced, right? Our copper is being kicked off. That's the only species that's being kicked out of a molecule. Since the copper is being kicked out, we can see that it has been displaced, it has been removed from the molecule on the product side, and cadmium has taken its place, giving us cadmium chloride and copper solid. Double displacement works pretty similarly, except there are 2 things now that are kind of swapping places. Like instead of just our copper being displaced, we now have 2 molecules. For instance, if we mix hydrogen chloride and potassium hydroxide, on the product side, we would expect to get a potassium chloride and water, or HOH. This is the result of taking the potassium and the hydrogen and swapping their places. So the potassium's being displaced from the potassium hydroxide, and the hydrogen is being displaced from the hydrogen chloride. So the two cations are both being displaced from their own respective molecules and creating new partnerships on the product side. So we can see the form of this displacement, or of these two different displacement reactions, is the same. We're just swapping cations. In the first example, though, we're only displacing one cation from a molecule, because the cadmium here is technically not in a molecule. And in double displacement, we are displacing both of the cations. They are both leaving their respective molecules. But the form, again, is the same. Last but not least, we have combustion reactions. Combustion reactions always follow this form. We have some number of carbons and hydrogens in what we call a hydrocarbon molecule. And these hydrocarbons are going to break down and recombine with oxygen to give us X number of carbon dioxides and Y divided by 2 numbers of waters, where the specific coefficients on the product side, this X and this Y divided by 2, come from the X and the Y in the hydrocarbon themselves. So if we're working with more complicated combustions, the forms of the X's, the Y's, and the Z's may or may not actually be properly totally fitting, but for the sake of having some variables here to actually represent a balanced chemical equation, we're going to need something. So X number of carbons with Y number of hydrogens are going to combine with Z number of oxygens, giving us X carbon dioxide, Y divided by 2 water in its most general form. All right, so we're going to be seeing these types of chemical reactions kind of all over the place. So it's going to be important to be able to identify, when working with the chemical equation, what form of an equation it is. This can help us to identify or even predict what possible products we might come across. So if you're told, like, hey, these two reactants are working in a synthesis type reaction, you would see the two reactants and be like, well, if I smoosh the two reactants together, what hypothetical products can I make? Or if you're told, hey, these two molecules react in the form of a double displacement reaction, all you need to do is observe the cations that are present, swap their places, and make some predictions about what types of products might be made. So these different forms are generally pretty useful to know. All right, so let's learn to write then these chemical equations. If you're told a reaction in the form of like words, if it's like a word problem, or if you're told like, hey, these things are undergoing like a synthesis, or if you have to infer that, like it's gonna be, again, really nice to be able to predict what types of products you're working with. Once you have a general form for your equation, then you can balance it. So let's learn to write chemical equations. You must have chemical formula of your reactants and products arranged in an unbalanced equation before you can balance it. Right, you can't just read a problem and be like, boom, got a balanced equation. Like there are some steps in between, and you're gonna have to take those steps to actually create a balanced chemical equation. So for example, let's say we're working with solid aluminum and diatomic chlorine gas, and we are told that these undergo a synthesis reaction to form some type of ionic compound. Let's write, ultimately, the balanced chemical equation. Well, this one we're going to work through together. We're just going to pick out the language in the wording of this problem, write it as we go, balance any equation that we come up with in an unbalanced form first. So let's start with solid aluminum. This is aluminum as an element with a solid symbol coming after it. This we would expect physically to be something like aluminum foil or aluminum shavings or like a block of aluminum. This is being mixed, hence the addition sign here, with diatomic chlorine gas. Diatomic meaning we have two elements of chlorine and these are in gaseous form. We are told that these undergo a synthesis reaction, so we're going to have to write a reaction arrow, meaning that these things will react. And since it's a synthesis reaction, we know that the two elements on the reactant side are going to combine in some way. And we're specifically told they make an ionic compound. Now here, it's going to be useful to remember what it means to be ionic. We have a combination of a metal and a non-metal in some type of chemical formula. So we're going to take our aluminum, which is a metal, and combine it with chlorine, which is our non-metal. And if we observe aluminum and chlorine on the periodic table, we're going to have to figure out what's the most stable form for aluminum and chloride to come together in. So if you were to take aluminum and put it in a chemical formula with chlorine, what are the subscripts that you would need to have to make a charge neutral ionic formula? Right, so everything that we learned back in chapter 5 is still going to be useful for us now. Now aluminum, if we observe its placement on the periodic table and determine its electron configuration, we would predict is the most stable in an ionic form if it has a 3+ charge. Chlorine, its placement on the periodic table and its electron configuration tell us that it would be the most stable with a 1- charge. Both of these charges would get aluminum and chlorine a complete octet. So if we want to mix aluminum with a 3+ charge with chlorine that has a 1- charge, we will need 3 chlorines and 1 aluminum in order to make a stable ionic compound. Right, so just because in a chemical reaction or a chemical equation like we have illustrated here, we see that we have 1 aluminum and 2 chlorines, does not mean we are going to make AlCl2. A stable ionic compound made from aluminum and chlorine will have to have the combination of 1 parts aluminum, 3 parts chlorine, and of course, because we are working with an ionic compound, the product will be in solid form. So this is our unbalanced chemical equation from the combination of aluminum and chlorine. Now this is, again, unbalanced, so we're going to write out some blanks out in front. These are going to be where the coefficients will go once we balance our chemical equation. In order to balance this equation, we're going to have to figure out how many aluminums, how many chlorines there are in each of these species. Aluminum as an element, has 1 aluminum, no chlorine. And chlorine as an element has no aluminum, but 2 chlorine atoms since it exists as a diatomic. Our product, aluminum chloride, consists of 1 aluminum and 3 chlorines. So here we can see that we're going to have to start scaling things up since we do not have a balanced number of chlorines on the reactant and product side. Now, because the chlorine gas on the reactant side is the only source of chlorine, and the aluminum chloride is the only source of chlorine on the product side, we're going to have to end up scaling these things up by a common factor. In other words, if we want to get equal numbers of chlorine on reactant and product side, we're going to have to scale up our numbers of chlorines by 3 to give us a total number of 6. And on the product side, if we want to scale up our chlorines to equal that on the reactant side, we're going to have to scale them up by 2 to also give us a total of 6. Since 6 is the first, right, the lowest common multiple between 2 and 3, this is going to be the factor we're going to have to multiply or scale each side up to in order to get an equal number of chlorines. In doing so, we also are going to change our number of aluminums on the product side, so we will also have to increase the number of aluminums on the reactant side. So the total now balanced chemical equation is going to read 2 aluminums, 3 Cl2s. These will synthesize together and create 2 aluminum chlorides. All right, so now that we've seen one of the reaction writing processes together, I would like you guys to try one on your own. So please write out the chemical equation, the balanced chemical equation for the combustion of propane. This propane is going to combust in the presence of oxygen gas and will create some gaseous carbon dioxide and water. So what is the balanced chemical equation for this reaction? All right, so our combustion reaction of propane is going to take the form of our hydrocarbon, C3H8, combining with a certain number of oxygen gas atoms. Our oxygen gases are always going to come in the form of O2. This is going to turn into a certain number of carbon dioxides, as well as a certain number of waters. And we can add the phases afterwards if we want. I admittedly was just a little too lazy to do it right here, since the focus is on balancing our chemical equation. Now let's balance this chemical equation by adding the appropriate number of stoichiometric coefficients. We're going to go the long way first and then compare this, our end result, to the previously stated generic form for a balanced combustion reaction. So numbers of carbons, numbers of hydrogens, numbers of oxygens. We're going to have, or we can see, a total of 3 carbons, 8 hydrogens, no oxygens underneath our C3H8, 0 carbons, 0 hydrogens, and 2 oxygens underneath the O2, 1 carbon and 2 oxygens underneath the CO2, and 2 hydrogens, 1 oxygen underneath the water. So a really good practice when balancing a combustion reaction, especially as a way to not have to memorize any specific forms, is to start with your carbon. So if we start with our carbon first, move on to our hydrogen second, the main motivation for doing this, for starting with carbon, moving on to hydrogen, and then doing oxygen last, no matter the form of your combustion reaction, is we can see that the carbon and the hydrogen are both in only one molecule on the reactant side and the product side. Like carbon starts in one molecule and ends in one molecule. Similarly, hydrogen starts in one and ends in one. The water starts in, or not the water, the oxygen, starts in one and ends in 2 different places. So this can make oxygen a little bit tricky to balance, and so we're gonna save it for last. All right, so let's start with our carbon first. We can see that there are 3 carbons on the left, only 1 on the right. So let's scale this up, giving us 3 carbons and now a total of 6 oxygens underneath carbon dioxide. Then if we move on to hydrogen next, we can see we're starting with 8 and ending with only 2. So we're gonna have to scale this up by a factor of 4, giving us 8 hydrogens and 4 oxygens underneath the water. Now this is again why we save the oxygen for last. The carbons and the hydrogens now are perfectly balanced, and so the equation can look complicated, but if we start with carbon and hydrogen first, we can save ourselves a little bit of time, because now at the end we can see that we have 2 oxygens on the left and a total of 10 on the right. Since we saved this for last, we can now add a 5 in front of our oxygen. This 5 being placed in front of our oxygen will scale up all of those on the reactant side also to equal 10, giving us a nice, totally balanced chemical equation. So if I went through that a little too fast, please, again, kind of rewind, rewatch this video, post any questions you have in the comments down below, or if you're in my class specifically, send me an email, please definitely do. Before moving forward, we're going to take this equation that we've seen, or that we can see now, and go back to our, here it was, general forms of our equations and compare it to our general combustion reaction here. So we can see that the subscript on our carbon, this X, turns into the stoichiometric coefficient on our carbon dioxide, and this totally just happened with us in our equation that we were balancing. Same with the Y on our hydrogen turning into Y divided by 2 in front of the water. So if we go back forward again, boop, we can see that the subscript of 3 on our carbon turned into a 3 in front of our carbon dioxide. The reason why this happened, though, we can see with the breakdown of our balancing of the coefficients down below. We started with 3 on the reactant side, and we had to scale up the number of carbons we had to match that. So we need to make sure that all 3 of these carbons are starting in our hydrocarbon and going into the carbon dioxide. Similarly, the subscript on our hydrogen, this 8, turns into 1/2 of 8 as a coefficient in front of the water. The reason why is, again, we need to make sure that all 8 of these hydrogens are going somewhere, and in order to balance the hydrogens in the water, which has 2 hydrogens per water molecule, are going to need half of the 8, which means in this case a total of 4. So we have X in front of the carbon dioxide, in this case 3, 1/2 of Y in front of the water, in this case 4, and then last but not least, the coefficient that goes in front of our oxygen is just going to be 1/2 of the combination of our elements, or element counts down below. So there's not really one really nice concise way to write what our Z is, but by observing the rest of the molecules, the rest of the atoms present in this almost balanced equation, we're going to take the total numbers of oxygens present on the left-hand side and divide it by 2. This is going to give us 1 propane plus 5 oxygens gives us 3 carbon dioxides and 4 waters. This is a perfectly balanced chemical equation, and as you, let's say, for instance, burn propane in the backyard for your grill, this is the chemical reaction that is constantly happening, eating up oxygen, pumping out carbon dioxide, and pumping out water vapor. All right, and that's it for part 1. So after all of our complicated discussions for geometries of molecules and intermolecular forces and our bonding theories, both valence bond and molecular orbital, it's kind of nice to have a straightforward lecture where all we're doing is just counting things. So here we have a couple of example problems pertaining to counting things and balancing chemical equations. If you have any homework, please take the time to pause and do your homework. And until next time, class is dismissed.